Thank you for coming back, and let's continue with the day, and it's time for the last talk of Code Dive in this room, and delivering the speech will be Douglas Crockford, who's here back by popular demand, so it is not his first time here at Code Dive. Just to remind everybody, Douglas is the author of How JavaScript Works. He was born in Frostbite Falls, Minnesota, but he left the place when he was only 6 months old because, let's face it, it was just too cold there. He has worked in broadcasting, learning systems, small business systems, office automation, games, interactive music, multimedia, location-based entertainment, social systems, and programming languages. Speaking of programming languages, he's the inventor of Tilton, the only ugly programming language, or the ugliest programming language that was not specifically designed to be an ugly programming language. He is also best known for having discovered that there are good parts in JavaScript, and that was perhaps the first significant discovery of the 21st century. With that, I'd like to leave you with Douglas Crockford.
I am so happy to be back, and I'm so happy to see you again. This is great. It's we haven't seen each other in a while, but the world's opening up again, which is pretty nice. So I want to start by introducing you to this wonderful woman. This is Jean Sammet. She was one of the first women to be developing programming languages. Brilliant lady. She was also involved in the first attempt to make communities out of programmers, to have stuff that went beyond a single company, kind of like what we're doing here today. She also wrote a book, which I really like, called Programming Languages, History and Fundamentals. I would highly recommend it, except it's out of print and it's really hard to find now, but it's a remarkable book. It's a survey of 120 different programming languages, in which she describes how they work and what they look like and the theory behind them. And the cover of the book is the Tower of Babel, and on each of the bricks is the name of one of the languages in the book. So that was just, she wasn't complaining that there were too many languages, she was just trying to show there are a lot of languages. And the book was published in 1969. Since then, the number of languages has just been going up and up and up. There are so many languages, and there are so many languages because they're so easy to make, particularly today where the machines are so big and so fast. You don't have the problem of trying to do a lot with a little. You can be really expressive. We have remarkable tools which do the parsing for you and do the back end for you. Most new languages offer little real value over their predecessors, except if you consider them as a learning exercise. Learning how to make a programming language absolutely makes you a better programmer because it gives you a better understanding of how your most important tool works. To get a programming language adopted requires extreme luck. It very rarely happens, but occasionally it does. One of the consequences of that is one clever programmer can make a new language, and then it will take an army of other coders to maintain it and extend it and to keep it fresh forever. Some languages don't become popular except with other language designers. Among those are Algol, BCPL, Smalltalk Scheme, and Haskell. It's usually believed that a programming language should only have one author, that if you have a committee trying to make a programming language, it just turns into a mess. That's generally true, except with these languages. These languages were designed by committees and are brilliant. That doesn't happen very often. The exception in that list is BCPL, which was designed by one remarkable man, but it was actually the first good parts language. So BCPL is the good parts of CPL, which was designed by a committee, and all the bad stuff you hear about designed by committee was in CPL. So the next language should promote a new paradigm that allows better solutions to current and future problems. So I'm associated with JavaScript somehow. I never intended to be the JavaScript guy, but I made a discovery that JavaScript had good parts, and so now I'm kind of a JavaScript guy. And the good parts are that it has flexible objects cobbled together with first-class functions with lexical closure, and that the language is optimized for event handling. That is absolutely brilliant. That JavaScript wasn't just better than we thought it was. It's better than all of the other languages for having that particular combination of features. Unfortunately, it has bad parts, including just about everything else that's in the language, including most of the new parts. One of the worst new parts is the sequential illusion confusion. And this is infecting a lot of languages today. It's become very popular, where you've got a program which is concurrent, which is doing lots of things out of time, out of order, but the source code is constrained to look like it's happening sequentially. And as a consequence of that convention, most coders do not understand what their programs do. They know what it's intended to do, but they don't know what it's actually going to do and when it's going to do it and how it's going to do it. And when we have a situation where the coder doesn't understand what his code is doing, that's when bugs happen. So JavaScript should not be the last programming language, and there seems to be some danger that it might be. And we can't let that happen, right? I mean, JavaScript has some good parts in it, but think about your children. You don't want them growing up and using JavaScript, right? We got to get past this for the children, right? So let me give you an example. Recently, TC39 added the WTF operator, which is spelled ? You know, my Tilton is a really ugly language. JavaScript seems on the path to compete with that claim. Anyway, the story behind this, the dot operator in JavaScript was wrong from the beginning. If you tried to refine a property from null or undefined, it would throw an exception, whereas the correct thing should have been to return undefined, so that you could build a path. And the path, if it can find something in the object, you get the value, and if it doesn't get undefined, that's exactly what it should do. That's what this one does. So this does the right thing, so I have to recommend always use this and never use dot. Except that I look at a program that's full of this, I just go, what the? It's so ugly. Did it have to be this ugly? So I wrote a book a few years ago, which you may have heard about a couple minutes ago, called How JavaScript Works. And in it, I described a new language called Neo, in which I removed every bad part of JavaScript, and Neo was sort of what was left over. And I also give you a parser and a code generator and all the tools you need to actually use Neo as a real language. Not that I would recommend anyone use it that way, because Neo doesn't add anything to JavaScript that JavaScript doesn't already do. So it doesn't fulfill my requirement of pushing us into the next paradigm, but it's a base language on which we could experiment and add new features and try to figure out how we get to the next language. So before we talk about the new paradigm, let's talk about the old paradigms. So in my view, there have been 6 of them in the history of programming. The first one is the introduction, the von Neumann architecture, where programs were written literally in machine code. You'd be writing an octal, probably, that you're actually thinking about binary as you're putting an instruction into each word of the computer. Next came symbolic programming, which we now call assembly language, makes that process a whole lot easier. And it was controversial at the time that it was introduced because management thought that computers were so expensive and people are so cheap. It's foolish to waste computer time doing things that humans could do. We don't think like that anymore, I hope, but that used to be a popular point of view. Next came high-level programming languages. So in the 50s, there was research that happened at IBM and at UNIVAC on automatic programming. The idea was that symbolic programming is just so difficult, we need to figure out a way to make it easier. And the goal was that the computer would write the program. You would describe the problem to the computer, and it would write the program for you. And the result of that experiment was called Fortran. Fortran is what we would recognize today as a high-level programming language. That what happens with each new paradigm is we raise the level of abstraction a little bit so that it becomes easier to do what we were doing before. And that's important. That's how we make progress. Although at the time Fortran came out, there were a lot of programmers who refused to use it on the basis that it didn't allow them to get down to the metal of the machine, and therefore they couldn't get the performance that they needed. Whether that was true or not, even if it was true, it didn't matter that as a programmer you were so much more productive. But the people this time who were opposed to Fortran were the programmers who would have benefited the most from using it. Next was structured programming, which started with Dijkstra's letter. Any Dutch people in the audience? Yeah. Do we like Dijkstra? Yeah. Any Dutch people who know who Dijkstra was? Yeah, good. We should know this stuff. Anyway, Dijkstra proposed that one of the problems with Fortran and similar languages was it used a go-to statement to affect the flow of the program. And he judged that that was problematic. And it turned out he was right. And that plus the algol language led to structured programming. And there was huge resistance to that. But eventually we determined that Dijkstra was right, as he usually was. And so we got rid of goto, although it took a long time to get rid of the goto. C and Pascal were considered the first structured programming languages, but they also had goto in it. So the designers of those languages recommended that you not use the goto, avoid it, but it was still in there because they didn't have confidence yet that Dijkstra was right. C++ made the same mistake. Java almost made that mistake. What Java did was it made goto a reserved word just in case they were going to have to go and put goto back in. They were hoping that they wouldn't need it. It turned out they didn't need it, but they were hedging their bets. JavaScript made the same mistake as well. I'm proud to say that it was because of my efforts that goto is no longer a reserved word in JavaScript. So we'll never get goto added to the language. That's one bad part that we will not get. And that was a big deal because there were a lot of people who were wanting to add goto back in. The next step up was object-oriented programming, which starts with the Simula language in Norway. Nobody took notice of that except for this kid named Alan Kay, who thought he could use that idea to make a programming language that was so powerfully expressive he could give it to children. So he called it Smalltalk. And that eventually led to object-oriented programming. Unfortunately, Smalltalk, although it's a brilliant language, did not become popular. Instead, C++ became popular. The major difference between C++ and Smalltalk is that Smalltalk got it right, and Smalltalk required that you understood what object-oriented programming was in order to use it. C++ didn't require that. Then finally, we're getting to functional programming. This started with the Scheme language at MIT. There was a brilliant guy named Peter Landon who was talking about it earlier, but nobody understood what he was talking about. But the Scheme language, people finally got the idea of how functions worked, and it was great. And the first language to bring that idea into the mainstream was JavaScript. And since then, a lot of other languages have copied JavaScript's example, and we're starting to slowly inch into functional programming, which is good. Now, one assumption that all of these paradigms make is that a program runs in a single machine. That's not how we work anymore, but that is an assumption that's baked into all of these paradigms and into all of the languages which are built upon these paradigms. So in our world, it's not one program in one machine. We have many processes per machine, and often those processes need to interact with each other. We have many machines which are interconnected, and so we have programs on different machines that need to interact with each other. The machines are now very fast. One of the assumptions in all of the old paradigm languages is that computers are slow, and so we have to make compromises in the design of our tools in order to accommodate that, in order to get adequate performance. Moore's law has completely obliterated that constraint, so we can think about how we program differently now. Machines have very large memories. In the design of C, they left out some really important stuff because their execution target for the machine was a mini computer that only had 16K. And so they knew they needed some features, and they just couldn't see a way to put it in. C++ just did that over again, and so it's like, we don't have to do that anymore. It's likely that your machine has 1,000,000 times more memory than that machine that C was designed for. That should give us license to think about things a little differently. Reliability requirements are getting increasingly strict as more and more of the world's economy and security get put into the computer networks. And insecurity is our biggest problem, that having all this stuff happening in one machine and having multiple machines interacting creates a huge attack surface. So I think the next programming paradigm should fit the distributed world that we now live in. And that is called the actor model. You've probably heard of it. It is not a new idea. In fact, the idea is 50 years old. It started as a conversation between Alan Kay, who was inventing Smalltalk, and Carl Hewitt at MIT. Kay was still trying to figure out what object-oriented programming was and the vocabulary for describing how things worked. And so he described the language as you send a message to an object. And Hewitt understood that, oh, what you're talking about is a subroutine call with indirection, which is a really clever idea. But what if you sent a message to an object? What would that mean? What would that be like? And so he thought about it, and he came up with the actor model, which was brilliant. And unfortunately, we haven't, or not enough of us have recognized the brilliance of this idea. And that's why I'm here to talk to you today. So I'm going to walk you through what the actor model is and how we might use it. And I'll caution you with this. There are as many versions of the actor model as there are people working with the actor model. It's kind of like how object-oriented programming still is, that every language has a slightly different idea about what object is. And people will still argue about, is JavaScript an object-oriented language? There are Java developers who will say, no, absolutely not. But, well, who knows? But anyway, so the thing I really like about the actor model is that its concurrency model, its communications model, and its security model all come from a single mechanism, which is message passing. Everything in the actor model is about message passing, sending a message to an actor. And it's such an incredibly expressive idea which accomplishes so much with so little. This is the kind of thing that can give us leverage on the complexity which is inherent in distributed programming. So this is how I think actors work. I come into actors from the perspective of all the work that I've done working with the web, and in the 2 startup companies that I founded, at Electric Communities, where we invented promises, and State Software, where I discovered the JSON Data Interchange Format. Anybody love JSON? Anybody? Yeah. Lots of hands went up. So in the actor model, an actor is a program running in a single process in a machine. An actor communicates with other actors only by message passing. There is no other way actors can communicate. There is no sharing even between actors in the same machine. So every actor has control of its own space, and no other actor can see into that space unless it's given a view as a result of receiving a message from it. An actor can create new actors in its own machine. Every actor has a private address. If you have an actor's private address, you can send messages to that actor. And if you do not have its address, you cannot send messages to that actor. Messages can contain private addresses, so you can pass an address in a message to an actor, and that will give that actor the capability of now sending messages to that new address. And actors can have state, which can change based on received messages. This is a limitation. There's a limitation in pure functional programming language that you can't have state. You can't have anything that's mutable. But in distributed worlds, you have to have mutability or it doesn't work. So incoming messages are queued if necessary, delivered in arrival order, just like browsers do with events. An actor runs when it receives a message, just as browsers do with events. An actor will not be given another message until it's done, just like browsers do with events. So if you're good at doing web development, either in Node or in browser UIs, you already have a lot of experience with the actor model, and it's not going to be a difficult transition for you to get into the new paradigm. If you're not, this is probably impossible, and the rest of this talk is probably not going to make sense to you. But if you have that background in the web, this should be pretty straightforward. So messages sent by an actor will be held until its turn is done. And an actor's turn may be time sliced, which means you can have a turn which wants to go on for a long time because you have a lot of computation that you have to do. You can just let that go, and other actors will still be able to continue to run while it's happening. You can't do that in Node or browsers because it's going to lock up the main thread and basically choke the system to death. So in that respect, actors are much more resilient and reliable than what we're currently doing. So the law of acquisition. There are three ways that an actor can obtain the address of another actor. By creation. So when an actor creates a new actor, it receives the new actor's private address. By construction, an actor can be endowed with a private address when it is created. And the important one is by introduction. An actor can receive messages containing private addresses. So I'm going to walk you through how all of these work. So the language that I'm currently developing I call Misty. I call it Misty because it's vaporware. It doesn't exist. It may never exist. I'm selling it to you anyway. I'm hoping it will at least be an influential language. Maybe someday it'll be a real language. But even if it never gets done, I'm hoping that the ideas behind it will get into the general community and will make progress maybe on other fronts. So Misty is built on top of Neo. So I'm adding just a few new features which get us into the actor world. First, I add a send statement. So you can send to a private address a message, which will be an object. And that object will be like a JavaScript object, except it can also contain blobs and private addresses. There's a special form of send where you can include a callback function. And so if the receiver of your message wants to reply, they can reply to the message. So we can get the old call response stuff that we're used to. That's pretty much the only mode that the web can do. But we also have that one-way send, which turns out is very, very powerful. Then you'll have a way to register a receiver function, which is similar to registering a listener. You can also register a portal function, which is a way that we bootstrap configurations of actors. We'll show an example of that later. So Misty offers a cleaner, more modular programming language or programming model, connection management, so you don't have to deal with any of that stuff, and failure management. We'll talk more about that later too. Failure management is really important in distributed systems because there are so many opportunities for things to go wrong, and we have to deal with it. Okay, so this is an actor, and I'm going to call it worker. It's a powerful actor. It can do a lot of stuff. So if you send it a message, it's going to go, and lots of good things are going to happen. And it's such a powerful object that we want to control who gets access to this one. So the worker creates an agent. The agent is just another actor running an agent program. And the white arrow indicates that the worker has the address of the agent and the agent has the address of the worker, which means they are allowed to send messages to each other. Now let's suppose on another machine there's another actor who's called a client, and that actor has the address of the agent, and it wants to get hooked up to the worker. So it sends a message to the agent saying, hey, hook me up. So the agent receives the message and decides, I'm not going to give him the worker because that's too powerful. I don't trust this guy. He's maybe at another company or at a division where we're competitive and we don't like them or whatever. For whatever reason, for good security discipline, we don't want to give it a direct connection. So the agent instead creates a liaison object or liaison actor, which has the address of the worker. And then it sends a message to the client containing the address of the liaison. So when that message gets delivered, the client now has the capability of sending messages to the liaison. This is called an introduction. This is a really, really powerful idea in actor systems. So the client, he's too busy to actually do his own work. So he creates a minion, and he gives the minion his address of the liaison. And so now the minion can send messages to the liaison, which will then forward them to the worker, and that's how the work gets done. Now, it looks like the liaison is just sitting in the way, but it's in a position where it can do a lot of useful stuff. One of the things it can do is attenuate the power of the worker. So it can be looking at the requests that it gets from the minion and decide, you can't do that. That's in violation of our contract, or that's something that you shouldn't have access to. And so it can constrain what's going to happen. So it can reject any request which it thinks is out of bounds, which means the worker doesn't have to be concerned with that. The worker doesn't need to care about accounts or permissions or any of that stuff. It just does its work. And it trusts the agent and the liaison to make sure that everything is okay. Now, the minion might want to get direct access to the worker, but it can't. There is no way it can get access to anything except things that it has the addresses of. There's no way it can find a direct route to the worker. So even if it's able to confuse the liaison, that's as far as its corruption can go. So the agent can decide at any point to tell the liaison, stop working. Our contract is done, or they have exceeded their limit, or they haven't paid their bills or whatever. And at that point, the minion's messages will get ignored and a revocation can happen. The agent might decide to create multiple liaisons, one for each client, perhaps. And so there are lots of clients that are connecting to the worker, each with its own liaison. The liaison can add to each message or can log for each message where the request came from. So we can match requests with the client so we can get accountability. So when we started this, the client had the address of the agent. So how did that happen? So let's back up a little bit. So one way that could happen is in an enterprise, you might have a directory actor who will contain the name and address of all of the entry points in your system. That's probably a bad way to do it, because it's probably going to rely on access control lists, and that's always a bad idea. And it doesn't scale globally. One of the things about the actor system is we can create environments where we have lots of companies that are all working together cooperatively under mutual suspicion, so they can all benefit from the interaction without having the ability to interfere with each other or tamper with each other or steal from each other. So, Misty provides another way of doing that. So we'll go back in time a little bit further. When the agent started, it created another actor called a portal. And the portal is an actor which can also open up a listener on a conventional network port. And so it's there listening. Now the client has the public address of the portal because it's on a well-known address probably. Maybe DNS will get you there. Or maybe they looked it up on Google, or maybe it was in a contract or a bill of sale or something that gave them access to that portal. And so there's a protocol. The client needs to know the public key and the address, the public address of the portal. It can send a message which contains its public key, which can be used to authenticate it, and any other tokens of standing or identification that are needed. And the portal can check that the client's public key matches the encrypted material that they sent. And if it decides everything is okay, it can then send a message back to the client with the address of the agent, and then we can proceed as we did before. And all of that, those two messages to set up a secure connection between these two machines and authenticate the two parties to each other, happens in one round trip. So let's talk about the worker and its minions. So it might be that the worker itself doesn't actually do any work at all. It's just an entry point, and it will distribute work to other actors. So there might be 3 actors that it relies on to do its work. And if we think about it the way we thought about doing things in the web, it would send a message to the first one and get a response, and then send a message to the second one and get a response, and then to the third one and get a response. But in an actor system, we can do things differently. For example, it can send a message to the first one, which will then take its result and send it to the second one, and send its result to the third one, and so on. And then when they're finished, they can send them back up the line again. But we can do even better than that. Because we've got these one-way message sends, we can just have the last guy send the message all the way back to an earlier guy. And so we skip the 2 in the middle. So that means we turn it around a lot faster because we're not doing as many network hops or message sends. And also those 2 guys in the middle are probably going to run faster, because often in these systems, we're not compute bound because the CPUs are so incredibly fast. More likely we're going to be IO bound or network bound. And we've cut half the traffic to those 2 nodes, so they're probably going to run a lot faster too. So this introduces another old idea that's called flow-based programming, where we can set up things that go between multiple processes and multiple computers in a way sort of analogous to Unix pipes, except we're not just sending one value through, we're sending a stream of stuff. And so all of this work just goes flowing and flowing through the world and getting processed and going where it needs to go. So you can make network topologies which match your organizational topology, so everything goes to where it needs to go. You don't need to centralize stuff anymore. You can distribute it. Another pattern is that we can send lots of messages in parallel. Because we're not stuck with the call return paradigm, we can send lots of stuff in the same turn, which means that all of those are going to run in parallel. And by doing more work in parallel, that's definitely going to improve our performance. So we have this problem with failure. So in distributed systems, well, even in the old paradigm, in the single system, things can go wrong. But when we spread it out, as we have been doing, there are more things that can go wrong, and that can be troublesome. That if you send a message to something and you're expecting a response and you don't get one, you don't know what happened. You don't know if they didn't receive your message. You don't know if their message was lost in transmission. You don't know that that server was just delayed because they're overwhelmed. Maybe they've got a denial of service attack going on. Maybe that's happening in your machine. Maybe they have a bug. Maybe you have a bug. Maybe they got hit by a Russian missile. You don't know what's going on. But you need to be able to deal with that. We need to keep everything running as well as we can get it to run. So the solution to that is something that Erlang taught us. That when something gets confused, we kill it. And anything which is dependent on the thing that we kill that too. And so we'll prune big trees and subtrees of the current actor space, and we'll inform a parent actor as to what happened, and it may decide to kill itself then, or it may decide, okay, I know what to do. I'm going to restart it and start it fresh. And that feels wrong based on our whole experience of trying to keep everything running, trying to get the 5 nines. But what Erlang figured out was the time when it's hardest to reason about what a program is going to do is when it's failing, especially if it's failing in a way that the programmer couldn't anticipate, if it's failing in a way that is impossible to test. The time when it's easiest to reason about what a program is doing is when it's starting fresh. So that's what we do. If things get in a bad state, we'll start fresh and pick up from there, and that works. So tying this all together is the actor protocol. On the network, an actor should not care what language another actor is written in. It only cares that it's talking the actor protocol. So we need this protocol, which is based on the SAFE protocol, which I developed at PayPal, which is open source, to replace the HTTPS system in actor systems. And we also need a JSON-like format, which adds blobs and private addresses to JSON. JSON, it turns out, is really good for distributed systems because it's a partial solution to the upgrade problem. In some forms of distributed programming, you've got programs that are written in different levels of a language or different versions of the code. And if the codes get out of sync, then things can fail. But if they're only relying on JSON, they're just getting an object which has fields with a certain name. And if there have been changes, often they don't cause any breakage. There might be a new field that you're not paying any attention to, or there might be a field that you're expecting that's not there. You can pick a default and keep going with that. It's not as destructive as some other schemes. Strictly speaking, a new programming language is not needed to enjoy the new paradigm. However, a new programming language will make it easier to think effectively in the new paradigm. And that ability to think clearly in a secure distributed way is critically important. So there are 3 ways to go forward. One is to augment existing languages to support the secure actor protocol. So your grandfather's language would still work. But you're still working with the old syntax, the old models, and I think that's going to just make things really hard. Instead, we could have a transitional actor language that's built on top of Neo and JavaScript, the Misty language. which is what I'm recommending today. We should do number 1 too, but it's more important to do number 2. And number 3 is actors all the way down. So Misty is basically actors made out of functions. Actors all the way down is actors made out of actors. Everything is an actor. And that's a really different way to think about stuff. Again, it's going to use the same protocol, so it interacts with everything else. And I've seen 2 proposals for CPU designs that will execute actor systems directly in hardware at the instruction set level, which is amazing. They're going to be very weird, very secure machines. I don't know when they're ever going to happen, so I'm not holding out. Misty is unlikely enough. I don't want to wait for those. So I want to launch a project. I want to launch an open source project to build the actor protocol and the Misty programming language and the actor bindings to, the old crappy languages like C++. You know what I'm talking about. So I call it the Theater of Computation project. It's nowhere yet, but I'm still trying to figure out how I want to organize it and how I want to host it and who I'd like to invite. And to help me figure it out, I'd like to call on you for advice. So if this makes any sense to you and you'd like to help pursue it, you can write to me at my email address, which is right there. Or if you'd rather do it in public, where I don't, because you want to, I'm on Mastodon, so you could go there at layer 8. If you want to see what I've written so far about this stuff, you can see my notes on the current design of the Misty language, which is almost certain to change, but it's mostly right. DEX64, which is the number type that's going to go into the Misty language. And the SAFE protocol is available on GitHub. So if this is of interest to you, I'd really like to hear from you. And meanwhile, I want to thank you all for coming. Again, it's so great to see you. Hope to see you again real soon. Thank you and good night.
Thank you, Douglas, for your wonderful speech. I think we need to do it again to wish Douglas luck in his new project. So once again, good luck to you, Douglas. Will you be happy to take some questions?
Yeah.
Yes. Okay, so we have some time for questions, please. So yeah, let's do it. The first question over there, please, in row number 4. And then anybody interested, you can raise your hand now, just for me to see.
Testing. Thank you for the great talk. I'm a sucker for Gene Samet. I own a copy of that book. Was very disappointed that APL only got a couple sentences in that book. But my question is, you mentioned Erlang, but Elixir seems to be a very a programming language adjacent to a lot of the ideas you talked about. Do you have thoughts, or have you looked into the Elixir programming language?
I think the idea of doing a new language on the Erlang platform is brilliant. So yeah, I'm a little jealous that they thought of it first, but there's a lot of brilliant stuff in Elixir.
Is there a big difference between what Misty would be trying to accomplish and what Elixir is tackling?
I think so. That I have a particular interpretation of the actor model, which they could do, but they're not doing that. I think there's a lot of similarity there.
Okay. Thank you for the talk once again.
Thank you. Oh, by the way, would you like a book? Thanks. Thank you.
There was a question over here, please.
So my original question was almost the same as as my colleagues about it was about how this is going to be different from Erlang and how this is going to be successful, where Erlang maybe wasn't as successful as some other languages. But also kind of continuing on that, how is this different from, what is the justification for the difference from what we have in JavaScript with workers? I know workers are not distributed, but they could be made to be. So.
Right. So first on Erlang. So Erlang did not set out to be an actor language. They kind of stumbled on it accidentally. There's so much brilliance in Erlang and the Erlang team that, but they didn't quite get all of the actorness. For example, it's based on, they don't have private addresses, they've got process IDs, and so those are guessable, so you don't get the same security. And there are a couple other things that they missed, but they got so much right. I very much admire Erlang. Workers in the JavaScript space do a lot right. So it's a separate process that you send messages to, that it sends back. That's definitely a good model. It doesn't implement actors in that you can't send the address of a worker to a worker and have it then send worker to the other one. And I don't think they're able to go onto other machines. So definitely the right idea. If you're working with workers, you've already understood a lot of what actors are going to do. In fact, for a while, I was calling my guys workers because of that affinity, and also because there are so many different opinions as to what actors were. I thought, I'll just avoid all of that confusion and just call mine something else. But then I thought, what the hell, I'm going to call them actors. So I'm doing that.
Perfect. Any more questions? Yeah, one over there, please. Over there.
Hello, very nice talk. Don't give me for confusion for this place, but where would be the boundary between actors and code that is running? Let's say addition of numbers doesn't seem like good actor. So what will be the threshold of when I should split things into actor and when not?
I'm really sorry, I didn't understand the question.
So what will be this, let's say addition of two numbers, or just a number doesn't seem like good actor. So number two, so where you would say is the threshold when the code start to become two actors instead of being just one?
It depends on how abusive you want to get. You could make a number an actor, and there's maybe some actor models which do that. Often in research languages there is a drive to make everything a thing. Like in object-oriented systems, there's going to be everything as an object. But there were, Java failed to do that because that was obviously inefficient, and so they have two completely distinct types of numbers which don't interact with each other well. One's fast and one's ridiculous, and but if you're talking about actor hardware where it's all the way down, they're probably not going to implement numbers that way. But it might be that in the language you could send a message to a number, and that message might say, add that actor to yourself and send me the result. So that's entirely possible. It's not what I'm recommending for Misty. I want something much more coarse. But if you want to go actors all the way down, that's available.
One more question over here.
Yeah.
Over here, center.
Oh.
Okay. I wonder if you have any thoughts on what could we do to help out debugging such actor networks. What would you think would be the best strategies to debug such networks, and what would be the tooling story, especially in distributed systems?
That's a really good question. So debugging is an open problem. Fundamentally, the problem is that debuggers want to have access through the network to stuff that we don't want to have access through the network. So there may be special modes. You know, you need a golden ticket in order to get a debug actor who is then able to break all the rules. That stuff is super scary, and I'm afraid some idiot web developer is going to leave that gate open and the system will get compromised. I don't know what the solution to that is yet. That's something we're going to have to work out.
Perfect, thanks very much. Any more questions, anyone? Okay, one over there.
Hello. So you were talking about new paradigm, completely new paradigm to create this new language. Do you think that there is still space for a new language in what you called those 6 old paradigms? Is there still a language that can be much better and become very popular? And
Possibly. Like we saw CoffeeScript take a run at that a few years ago, and for a time all the hipsters were using CoffeeScript. But that seems to have gone out of fashion now. So a new language based strictly on fashion, I don't think is probably a good idea because fashion can change so quickly. If you could figure out a way of making a language much more expressive, like if APL was another ugly programming language, but it was incredibly expressive, because you could apply operations to arrays and do a whole lot of stuff with very, very little effort. If we could maybe take that kind of stuff and put that into a conventional language so that it would be less cryptic and easier to maintain, but still provide the performance benefits of APL, something like that, even though it's in the old paradigm, might be worthwhile.
Okay, perfect. Thank you very much. Douglas Crockford, everyone.